Today I start the time-dependent perturbation, chapter 14, time-dependent perturbation theory. Introduction. Basically, we study the perturbation theory as the Hamiltonian is that solved Hamiltonian plus and the perturbed potential. But in previous perturbation theory, in this interacting potential is not time dependent. Basically, in the classical mechanics, and potential should be time independent, because time dependent potential, energy is not defined. Energy it means that time dependent potential means that energy dissipation, so it is not defined the energy. But in Hamiltonian and in general, and the time dependent potential can be considered, because, for example, when you apply the magnetic field or electric field, it is oscillating vector potential or the scalar potential. Especially vector potential should be time dependent. So in most cases, so and potential should be time independent to make energy conservation. But in general, and here we assume that we'll deal with the potential as a time dependent potential here. It is not basically, and this, if we think that time dependent potential, the energy is not defined. The potential should be only time independent. But in here, and the Hamiltonian, it is not energy but Hamiltonian, and Hamiltonian can deal with the time dependent potential. It is not anyway, and the Hamiltonian is different from the energy. Here the H0 and n epsilon n in n, and the eigenvalue is well defined. So in this and also we assume that this Hamiltonian satisfy the Schrödinger equation h psi, and here this wave function should be time dependent in this case, and we only consider for the stationary state time evolution, but the time dependent, but it is a stationary state. At the final, it means that the final state is the stationary state. Then it is IH bar partial t and psi st. It should be satisfied the time dependent Schrödinger equation. Here, let's take the psi 0 t is that initial state wave function, and initial state wave function is that 0 initial state, and time equal to 0, and evolution is the exponential minus psi ht over t, and it is a time evolution factor. So in the complete set, this one can be write down as the exponential minus I ht over h bar, and n it is complete set, and the psi 0 0. Anyway, it is Hamiltonian. It is operator, not a eigenvalue, but this exponential function can be expanded as a polynomial function, and this polynomial can be applied to the n basis vector. Then becomes to this Hamiltonian can be write down as the energy eigenvalue. So, and expanded as a polynomial infinite series can be also remake as an exponential function. So if we can write down that exponential minus I H becomes En because energy eigenvalue n psi 0 0. Anyway, then this term, this one is the any kind we can deal with it as a coefficient because it is any kind of the initial state wave function is observed at the end state, so we call it is a coefficient Cn. Then when we apply this wave function in both sides as m and psi 0 t case, then when we apply this and exponential minus I epsilon nt and m psi 0 like here, because here when we apply the this one, and also it means that m n psi 0 case, and it makes that Frank delta mn, so it makes that the summation n, it becomes that m psi 0. Okay, so and this makes that the m state expectation can have this form. So and when we make the square means that the probability, and the probability at time t is identical with m and psi 0 0 because in mathematical point of view, and this exponential equal to 1 because the multiplication of the complex conjugate, but in the physical point of view, and it is conservation of particles because it's a probability at the time t, and it is a probability at time t equal to 0, so it means that conservation of particles. So in the above, we say that it is n and psi 0 0 is the coefficient Cn. So here when we go back, here and here, then in the psi 0 t equal to summation to n and the Cn and n and the exponential minus I epsilon nt over h bar. It is anyway it is a wave function at ground state. So and we can think that it is at time t equal to 0. And the Cn is a known variable, it is coefficient, and we should determine this Cn because it is an n state, and we should consider all about the possible quantum state, and also corresponding energy eigenvalue can be considered. So it is this one makes that the time evolution, so it is the time above the wave function. Here it is a first interaction picture. Here we solve the stationary state wave function. If we know that it is a stationary state wave function, then the Hamiltonian applied to the h0t over h bar, then we call it is the interacting with the Hamiltonian. So we call it is interacting wave function. It means that stationary state wave function becomes the interacting wave function by applying this Hamiltonian, because this Hamiltonian makes that any kind of interaction it acts as an interaction term. So then this stationary state wave function evolves to the interacting wave function. So also in previous case, and we should think about that Schrödinger equation, and the Schrödinger equation includes the IH bar and partial t. So let's think about that this time derivative. Then the first time derivative with the exponential, it appears that I h0 over h bar. So I becomes minus, and h bar cancel with each other. So it is minus h0 exponential I h0 t over h bar and psi st. And also differentiate with the other this psi s. Then IH bar exponential I h0 t over h bar and partial t and psi st. In previous case, and we say that this stationary state wave function satisfies this Schrödinger equation, and the H means that H0 plus potential. So it is minus H0 exponential I H0 t over h bar psi st and plus IH bar exponential I H0 t over h bar and I'm sorry, I include IH bar. So IH bar partial t becomes the H0 plus Vt and psi st. So here minus H0 and H0 cancel with each other. So it makes the exponential I H0 t over h bar and the potential Vt exponential minus I H0 t over h bar psi I t. So here we denote as the here it is interacting potential. So it is IH bar partial t psi I t becomes, and it is Vi t and psi I t. Here we already discussed that interacting potential is that time-dependent potential in both sides and the exponential minus I h0 t over h bar and the exponential I h0 t over h bar. It should be applied here. So, and also let's remember this formula. In the interacting wave function also can be written down in complete set expression and psi I t. Then it is that summation n exponential I h0 t over h bar and psi st. Then also this Hamiltonian exponent Hamiltonian also becomes the energy eigenvalue. So summation n exponential I epsilon nt over h bar n psi st. And when we think that this one, and it makes that for summation to n is that Cn n exponential minus I epsilon n t of h bar, because and psi st anyway, and here from this formula, so and it is 1 current delta nn, so and it becomes the Cnt and the exponential minus I epsilon n t of h bar. So these two exponential cancel with each other, so it becomes for the summation to n Cn t n state. Here Cn t is that n and psi I t. And anyway, then it is, when you think about that interacting potential, time-dependent interacting potential, and it satisfies this kind of expression here, and also we should write that here psi it is that like this. Yeah, psi it also can be write down like this. Then it is, secondly, let's think about the time evolution operator. And here let's define that the time evolved operator and interacting wave function has the interacting wave function at t equal to 0, initial state wave function, and any kind of, we do not know that detailed expression of the time evolution operator, but let's denote that as the t and t0. Here it is, we call it as a time evolution operator. This time evolution operator makes that time evolution from the t equal t0 state and t state. So this evolution operator makes that wave function, initial wave function, makes that the final wave function, but we do not know that the detailed expression here. So, and when you apply, and here this time evolution operator t and t0 apply to x and x prime, and we call it as a propagator. Propagator means that at t equal t0 state, x state, and the final t state, and it becomes the x prime state. So, and the time makes that after some time at t minus t0 or later, and initial x state becomes the x prime state. So it is, we call it is a propagator. Here, let's make that detailed expression of the time evolution operator. So, and let's think about that the time derivative with the psi it. Then at first, actually, then the time derivative apply to only the time evolution operator, because it is initial state, just only the initial state t0, but it is not time dependent. So only apply to the time derivative to the time evolution operator. And also psi I t0 is that just only initial state. So Then here, and let's think about IH bar partial t psi IT here. Then it is IH bar partial t UI t0 and psi I t0. So, and from in the above, we already know that this one makes that here, and it means that the Vt. So it makes that Vit and psi it. And psi it also Vit and ui t0 psi I t0. So from this, here IH bar partial t ui t and t0 state, it makes that Vit and ui t and t0. Here, and IH bar partial t here, IH bar, then the IH bar here, and Vit0 is that same state. Then it makes that here VI UI. So from this, and we can calculate as that dui over ui equal to 1 over I h bar and Vit dt. So when we integrate in both sides, and ln ui equal to minus I integration and Vit dt, and from the t0 to t prime state, and here t prime. Okay. So from here, let's make that here t0 and t0 means that there is no change of wave function, so it should be 1. So from the calculation, and t and t0, it makes that at the t0 it is equal to 1 and minus I over h bar from the integration t0 to t and Vi t prime, and also and ui t prime and t0 and dt. Yeah, so then it is also makes that from this expression, and it is a self-consistent equation, so it also 1 minus I over h bar integration from t0 to t prime and Vi t2 prime and ui t2 prime t0 and dt 2 prime. Okay, so and here it makes that 1 minus I over h bar integration t0 to t Vi t prime dt prime, and secondly, and plus minus I over h bar square from t0 to t dt prime and Vi t prime, and integration from t0 to t prime dt2 prime and Vi t prime t2 prime, and like this, and so on. Here, and this time evolution operator, it is infinite series like this form. So here we find that anyway it is let's remember this time evolution operator expression. Then we define that, let's define it as the time evolution of the exponential minus I of h bar integration to t0 to t prime dt prime vi t prime. Here t means that it is a time ordered operator. Time ordered operator. For example, t applied to a operator and b t prime, then it is the a t b t prime. For example, t is later than the t prime. For example, it means that t prime it is earlier time and t is the later time. So it is ordered between the t prime. It is earlier time and the later time. But in other cases, for example, t is earlier, t prime is later, then changing the operator, be t prime and a t. But in this case, and plus minus should be considered. And here, plus case, it is bosonic particle, and the minus is a fermion. Because in fermion case, and by changing two wave function makes the antisymmetric wave function makes that minus sign, and so plus is the bosonic particles, and it is a symmetric wave function, so it is a plus.